Okay, let's elaborate on last video and where we looked at the relationship between uh, voltage, current, and resistance. And so here again we have 15 volts that's measured across our load like this on each side of the load. So we're measuring the entire voltage being induced on the circuit. And then through the circuit, we are measuring our current, measured here in milliamps. And, we got 15 volts and we got about 10 milliamps. And that was with a 1.5 kilo ohm resistance. So let's just put that up as the formula, and that's I equals U divided by R, and so we had 15 divided by 1500 ohms equaling about 10 milliamps. So that's what you can see here from the gauges in our setup here. Now let's take this a little bit further about series and parallel. And really the fundamental idea behind this is a law called Kirchhoff's law. But let's just see what it does instead of getting really theoretical and philosophical here. So let's quickly just turn our power off so we don't have any crazy connections during this. And so what I've done here is that I've taken two of these resistors of 1.5 kilo ohms, which is the same as 1500 ohms, and I put them in series with one another, so connected after one another, like this. So let's see what that does to a circuit. So we're going to connect that entirely the same way. So this just we can see it very clearly. Here we go. So we got power coming in here, and then we want to measure the amps going through the circuit by serial connecting it with the power. All right, then let's measure some voltage also in this circuit here. And first off, let's measure all the way across this entire circuit. All right, let's put a 15 volts back on and see what just happened here. We have 4.8, I mean, pretty much 5 milliamps. Pretty much 5 milliamps. So let's see what happened to the resistance from this, because it seems like something happened there. Something had to change, yeah, besides the amperage, because the resistance determines with the voltage how big the amperage is going to be. So let's analyze this. So we got resistance equal U divided by I. And in this case here, we still at 15 volts. And I went all the way down to 5 milliamps. Which is also the same as 0.00. This is the 100s, this is the 10s, and this is the 5s. So this is how many amps that it is. So let's divide that up to one another. So that went up to 3,000 ohms. Also the same as 3 kilo ohms. So, and these were 1.5 kilo ohm resistors. Now the circuit, by being in series, got doubled. All right, let's see if it's the same throughout the whole circuit here. So we got 15 volts across these two resistors. And what's interesting is that if we take and place the voltage difference between the two, we have 7.5 volts. And so that way, between these two resistors, we now have split the voltage. And that proves Kirchhoff's first law is that the sum, if we have more resistors, this will keep on like dividing the voltage like this, not evenly, only because we have two even-sized resistors. Like if I brought in our 3.3 kilo ohm resistors, why don't we do that? Let's see what that does. 1 second here. Let's take off the power. All right. And then let's go all the way across here. All right. Let's fire it up. Boom. Huh. Even lower. Even lower. So now we're down to, and our original resistor that we're measuring across is only 3.5 volts. But we know there's 15 volts on this circuit. So interesting. So by adding another resistor, a 3.3 kilo ohm resistor, we now have lowered even further our current. But that's, that's not that surprising. We already figured that it was lowered here by adding another one. So adding another, the more resistance, the lower our amperage draw is. But look then at this here. Our voltage across that resistor that we now measured before has even further lowered. And so let's see what happens if we measure across our next resistor, which is the same size. So it has that voltage as well. It has that same voltage drop as the one before. Let's measure them across one another like that. 7. So those two together, you can just add together, and you got 7. But where's the rest of the voltage? So if we measure all the way across the circuit, we're back up on our 15 volts. We had 7 here. Well, let's find where it went. Oh, sorry about that. And here's the rest of it on our last resistor that we just added. So what Kirchhoff is saying is that the sum of each individual voltage here is equal to the overall voltage. So let's call them some names here. So R1 is this guy. Let's write it right here actually. So R1, R2, and R3. All we got to do here is just add them up, and we got our total resistance, and it goes the same for the voltage as we could see. So we can call that U1. That's the voltage that's going across here. U2 plus U3. Because like we can see here, we got on U1 we got 7.8. And let's go back over here. These two fellas here, that each had about 3.5. Let's see. Okay. Again, there's some leeway in this. It's not super accurate. So all right, let's put this. And then so 14.8. I mean, pretty much 15 volts. We're at 15 volts really. So we saw that the resistance, by being increased in series, lowered our amperage, and that each individual voltage is the sum of the total, and the biggest voltage drop would be over the biggest resistor. Okay, well, so that was Kirchhoff's first law. Now, what happens now if we take our two 1.5 resistors that we originally came with, two of these guys, and put them in parallel like this, put them across from each other? We're still going to have some power coming in, and that's going to go through our multimeter as a closed circuit there back. And now let's measure across these two guys here. Let's put some power on. 15 volts. Let's give it a notch more here. And look at that. 20 milliamps. So something happened here. Something happened here. Because the original setup, as you remember up here, on one of these resistors gave 10. So that makes sense. By increasing basically the accessibility of electricity from passing from one side to another, we made it easier. So now more current can run. And that's what happened in this case. The calculation of this is a little bit more hairy, but it's not too bad. So in order to calculate this total resistance, we need something called reciprocal values of these. And let's see if I can make that as simple as I can. Okay, so a reciprocal value is by dividing it by 1. So we got a 1500 ohms, or 1.5 kilo ohms, which is the same. And how we put those two together when we're talking parallel, we're still saying plus, and then the reciprocal value of the other resistor, which was also 1500 ohms, nice and easy. And what we want, once we have these reciprocal values, we want to get the reciprocal value of that. And so what that translates into in real numbers is that first we got the big guy over here with reciprocal value, and this number here, so it's 1 divided by 1500. It's going to give a really small number, and it does, and that becomes 1.000. Oh, I'm sorry, I can't read here. 67 plus, and then the whole thing over and over again because it was the same value. 67. These two together is pretty simple. I mean, these are very raw numbers, but you get the idea. Here you just need to use a calculator, of course. And oh, wait. This is what you get out of it. And when you take that and divide it up into 1, you get 750. We're getting further and further over here. So 750 ohms. Interesting. And so when we look at this formula up here, okay, we had 15 volts. So we want to calculate our current, see if it makes sense with the 20. I U divided by R. Our U, that's our voltage, was 15. We calculated here that our resistance is 750. And now 750 up into 15. That gives us 0.02 amps, which is also the same. And so this is the in milli, which means 1,000. Then we got 100 here. We got the tens there. Let's look at that. 20 milliamps. So what Kirchhoff is saying in this case, let me show something first. Let's see what happens here if we now tag on our serial network here of resistors. The two serial guys here. And let's turn off the power. Disconnect here on one side. We're going to tag on this circuit here. And then close our circuit with power to our, all right. Okay. Let's put some power back on and look at our current dropped way down again. And so what's I want to show you here is how the voltage is being, we remember from the voltage dividing that the biggest voltage drop will be over the biggest resistor, because in our previous example from the serial connection, we remember that half the voltage was dropped on R1, which was a 3.3 kilo ohm resistor. So let's see what the voltage drop is over a parallel connection here. Well, that's only 3 volts. So out of the 15, so the voltage drop is very small. But what's interesting is that it is the same over each of these resistors. So what the parallel connection is doing is that it's dividing up the current. And so the easiest way to explain that, how it does that, is that the current will go where it's easiest to go through. And so you're going to have the highest current draw through the smallest resistor. So where the power has the easiest time to go through, which is the lowest resistance, it's going to have the highest current. And so let's analyze that. So in this case, we have the same on both sides. And like you saw here up here, that made the exact half of the resistance of 1. So we will have an even current load on both sides. Our voltage is not significantly high, but so let's look at that. 3 volts divided by our 4 milliamps, give or take here. We can now calculate in the opposite direction 750 ohms. So it all makes sense. And so the total resistance of this circuit is going to determine how much current is on the entire circuit. And then from there, we can start to analyze where each power is going according to our Ohm's law. And what's interesting about our parallel connection here is, again, the current is going to primarily run where it's the easiest for it to get through. So if we changed one of our resistors here to half of it, so let's analyze that. We're going to maintain one at 1500. And we're going to lower the other one to 750. And then we're going to break it down into our reciprocal values. Divided by 1. Again, we need the reciprocal value of it. So now our total resistance on that circuit is now 500. So as you see, now it's not a even halvening of the resistance by putting in another resistor, and then now we can analyze how much current that goes on each resistor by using Ohm's law again. And we know there's 3 volts, and the 3 volts are present on both sides in this parallel connection on either one of the resistors. That's going to remain the same no matter what side you're measuring on. So we know it's 3 volts. So we're going to use I equal U divided by R. So in this case here, that'll be 3. And let's do it for, let's call this resistor here R1 and R2. So that's 1500. So 3 divided by 1500. Here we go. And that's the same. Remember, this is hundreds, tens, and ones. So we're all the way down to 2 milliamps here. Same as that. Let's look at our other current. 3 divided by 750. Well, no, that's going to be, so that's going to be double of that. Four milliamp. So that's interesting. So our smallest resistor, as you can see from our calculation, is what's going to draw the highest current. And so let's look at what this circuit altogether is doing, because we know that we have one resistor of 1500, 1.5 kilo ohms, and then we got one of 750 now, and we found out up here that that's a total of 500 ohms. So let's analyze that guy the same way. We're almost running out of space here, huh? 3 and 500 is 0.006, same as 6 milliamps. So what's really interesting is, look at that, is that 2 and 4 equals 6. So that's the conclusion on Kirchhoff's second law, is that the currents going to a junction on this guy here, on a parallel couple, the current that is running on each side here is equal to the current that's going to be coming off of it. I hope this made some kind of sense. Please comment below if you want me to clarify anything. Thank you for watching.